last class I think we were discussing about finite element method. We just like started discussing about FEM and like uh, before that we had already discussed weighted residual methods and Taylor risk method, etc. Those are like the global methods for finding approximate solutions of PD, and these are like more of the like more conventional CFD methods where we break the domain into like finite number of pieces and like at each uh, the subdomain that we get, we solve our equations and finally get the solution. So that also let's like recap a little bit what we were doing. So we were trying to solve the conduction equation, right? The steady state conduction equation with the source. So we were trying to solve this, and as we had done previously, also we will take an integral of this, but not over the whole domain as we were previously doing, but over a finite element. So we can, if we have our domain from let's say x is equal to 0 to some x is equal to L, then we can like divide it into different elements, and we would uh, solve for each element and then finally assemble our solutions to get a global solution. So we just took one such element. Let's say its endpoints are I and J, and this is the element E. So we were talking about one such element, and what we did was simply like arrive at the weak form uh, for this particular element, which will look like this IJ. So yeah, the weak form will be so. This is the form as such, and yeah, and other than that, we will have the source term. I give. So this is the linear term, and this is the bilinear term, as we had discussed before in the weak form solutions. So other than that, there will be boundary terms, and we had, I think, like discussed, we can have like the heat so fluxes. Since here we do not know the boundary condition, so like if we take a random element, so the in for that particular element, we might not know the exact values of heat flux. So when we are assembling it, we might try to figure out what the boundary conditions might be. So we were just simply like taking heat flux at I and heat flux at J. So I think we arrived at a question like this. So this is a certain equation that we arrived at, and then we what we have to do, we have to take a trial function as we were doing in our previous methods as well, weighted residual methods. We will take a trial function. So the trial function that we took had this kind of a form: NITI and plus NJ TJ. So here, what is NI and NJ? NI and NJ are called uh, these are called the interpolation functions. So we like take this Ni and Nj like the matrix, and we will, let's say this is n transpose. We define it like a matrix, and this bit is of this form: x minus x share, xi minus x share, xi minus x divided by xi. So the way that this is designed is that this is first of all linear. So this both the term ni and nj, they are linear. They only have like x and coefficient. And another thing, it is that if you put x is equal to xi, then this becomes 1. And if you put x is equal to xj, then this becomes 0. Similar for like nj as well. If you put x is equal to xj, then this becomes 1, and x is equal to xi, this becomes 0. So if we add additional points to the to an element in finite element method, it will always follow this rule that the interpolation functions will be 1 at the node that it represents, and it will be 0 for all other nodes. Okay, so that is basically like a way in which we represent this like functions. So these are basically trial functions. These are nothing but trial functions. So these trial functions are taken in such a way that it has this property, and what it helps us to write our trial function like this. So this is Ni into Ti and Nj into Tj. So if you remember, in weighted residual methods, we were attempting to find some uh, parameters. We were trying to evaluate some parameters. We are taking a trial function which has certain parameters, and by using this weak form, we were trying to make an estimate of that parameters. Instead of making an deriving a whole solution, we were like assuming a form of the solution, and we were evaluating some parameters. And in this case, you can see that the parameters are nothing but Ti and Tj, which are itself the temperatures. So we are directly trying to find temperatures at certain points in the domain, using which we can evaluate temperature at all points in the domain, an approximate value at least. So that is basically the whole idea. So uh, the notation that we have here used, we will convert it to a matrix form, and it will be easier for us. You will see that this will be easier for us. So notice I have taken n transpose here. So this makes this n, and this makes this t. So t has been defined like this. EINTJ. Now we will be using Galerkin's method. Here we will be using Galerkin's method. So in finite element is basically a form of Galerkin's method. What happens in Galerkin's method? We uh, take W uh, by an inspiration from the trial function. So we have these interpolation functions which are used to define the trial function, and we will do the same for the weighting function. So let me simply write it down. We had discussed this very briefly in our previous class. So we had this. The reason for writing like this in the transpose form and this like in a straightforward way will become very clear when we substitute this. So now what we have to do is basically take this and take this. So this expression and substitute it here. So if I substitute it here, let me write one line here, integration ij. So if I substitute here, so W is nothing but an arbitrary like set of parameters. So we do not really care right now what is W, and you will see that the W will actually cancel out the whole equation. So we would not even need to like find or assign any value to this W. So we will have this W transpose. This is independent of X, so it can come out of the derivative. However, what is not independent of X? N is not independent of X, so that will remain. So this becomes N transpose dx. K will be there. This K is there, and when we substitute T, the N comes first. So this is dx of N. T will remain, but T will not be under derivative because these are parameters. So these are not dependent on x. These are not functions on x. These are basically the way we have defined it. These are basically temperatures at the two node points, so which are not independent of x. Dx, and this side we will have ij. So W transpose will be there, N transpose. S is a scalar, so S will remain dx. So this was the source term. Now we have this. So what is Wj? Wj is nothing but like this capital Wj, and this is Wi. So that is also nothing but capital Wi. So if we try to write this in matrix form, this will simply become W transpose, and what will remain? Minus I and Q double dash J, that will be positive. Okay. We have done nothing but just simply substitute this in this matrix form that we had defined. Now, what happens is if we define it like this, we can see this W transpose as a matrix actually cancels out. So if we had not defined in this matrix form, we would not be able to do this. But since we have, we can cancel this out. We do not, like, each term has this W transpose, and it can be taken arbitrarily. So we can simply get rid of this. Okay, so I will write down the form that we have got right now in the next page. So I, J, we have this B, N transpose dx, K, D, N dx, dx into theta, T. So I can take this T out of the integral as well because this is independent of x. So that's what I have done here. And what else? What else? Here we see that we have this integration on N transpose. So S also can be taken out because it is not dependent on x as of now. We have not taken it to be dependent on x. So what remains is N transpose dx, and this flux terms remain. These are the boundary terms. So now we have found out a simplified version for one element. So this is just for the element E. Now we can try to assemble this. So let's say we have three elements, as we had. Let's say we have three elements. So three elements will correspond to four node points. So 1, 2, 3, 4. These are the node points, and these in circle, these are the elements. So there are three elements. So let's say for this first element, we have found out this matrix. So this is a matrix, right? This n we had defined it like 1 cross 2. So n was defined as 1 cross 2. So n transpose is nothing but 2 cross 1. So multiplication of this, you see, will give you a 2 cross 2 matrix. T is nothing but 2 cross 1. Again, n transpose is nothing but 2 cross 1, and you can see this matrix is 2 cross 1. So this is a matrix equation of 2 cross 1, and you will have a square matrix here. So let's define this as K1 for the element 1. So this is for element 1, and we will have this T as T1, T2, and let's say this particular source term, let this be F1, F2, and we will definitely have this minus uh, plus U double. Okay. We can find this K1, all the elements we can find out. Simply what we have to do is for example, we want to find out this K matrix. So we want to find out K11. So this, okay, let me, okay, just for the sake of it, let me not write K1 like this. Let me write this super exponent. So how you will see, if I have this K1 matrix and let's say K1 1 1. So this is a 2 cross 2 matrix. Sorry, K1 1 2, K1 2 1, and K1. So how can you find this out? What will be K1 1 1? This will be nothing but uh, so point 1 to 2. So this is node points, node point 1 to 2. This will be d dx of n1 and d dx of n1. So this you can find out. How? You will simply substitute your n1's expression. So n1 will be this. So x minus x2, x1 minus x2. So this will be your n1, and you can substitute it here to find out the expression. You will get a very, like, you will get a value. So for similarly for K22, K122 also you can find it out. And what about this? These two will be actually equal because this is a bilinear symmetric matrix we have already discussed. So this will be equal to this. Hmm. So these two will be equal. So this is a symmetric matrix. Hmm. So this will be a symmetric matrix. So this you can figure out. Hmm. Anyways, this whole thing is still just for element 1. Now, so similarly, we can find out about element 1, we have found out, we can find out element 2, and we can find out element 3's equation as well. Hmm. Now, when we are assembling it, when we are like, what we have to do is we have to solve the whole system together. Hmm. The reason, the reason being that we actually do not know this boundary condition. We do not know. We might know Q1 dash double dash, but we definitely do not know Q2 double dash. So that's why we will try to assemble this. And what will happen when we try to assemble this? So let's first write down the unknowns. T1, T2, T3, T4. These are the unknowns. So this is my T matrix. This is my T matrix. So I have written this down. So this will be equal to, so this is like, let's say for the first element, this is for the first element. So you will have this F1 of 1. So for the node 1, which element is contributing? Only the first element is contributing. So you will write F1 from the element 1. From for point 2, which elements are contributing? Both element 1 and element 2. Both are contributing. So So here I will take for node 2 from element 1, and also I will take the node 2 from element 2. Both I have to take. So I will add these two. Similarly, for node 3, element 1 plus for node 3, from node 3 from element 2 and from element 3. You see, node 3 is connected to both element 2 and 3. However, node 4 is connected to only one element, so that will simply remain there. So this is connected to element 3. Okay, so this is my F matrix. Okay. I know like this might be a little heavy. Like if you have any like doubts or like if there is any problem in understanding, please like you can ask. Hmm. If there is any problem in understanding any of this portion that we are doing, because it is very important to understand this. FEM is a very important methodology um, that is used everywhere and like will be used in this course as well. So and this kind of like assembling of matrices, these are also very important concepts in CFD. So if there is any like problem in understanding, please let me know. Okay. So far what we have done, so far we have like written down our unknown matrix, and uh, we have dealt with the this F. So this is a column vector, F column vector we have dealt with. What about the this fluxes, heat fluxes? Heat flux, you will see something interesting happen. You will see that you will have this minus Q1 double dash, and from element 1 in the point 2 you will have this plus Q2 double dash, and since the same heat flux will be entering into element 2 as well, you will have minus Q2 double dash. So this will be 0. Similarly, for third point also you will have plus Q3 double dash and minus Q3 double dash, and that will give you 0 as well. So all the points in between will have 0. Only the endpoints will have uh, some fluxes remaining, which can be given as boundary conditions, basically. So this is there. So this basically simplifies our problem that we were like facing, that mm, uh, the any element in between, we might know the value of we might not know the value of fluxes, but when we are assembling, we are seeing that the fluxes actually cancel out, and only the uh, fluxes for the endpoints are required. Excuse me, I got a cold. Uh, yeah. So Uh, along with this, we need to also uh, find out the equivalent matrix for this stiffness matrix. So K also we need to find out an equivalent matrix. So we have seen what happens for one element. We have written it down here. We get a 2 cross 2 matrix. While assembly, here also we will see like we have this K11, K12, K21, and K22. These are from the our element 1. So this will remain, and the second element will actually contribute to this K22. So there will be one K22 from the second element as well, and you will have subsequent points. Okay. So you will see in this particular case the diagonal elements which are not in the extreme points, like not 1 and 2, but 2 and 3, K22 and K33 will have some overlap. So they will have contributions from both element like preceding it and after the element which comes like right after the node. So we have to keep that in mind, like which elements are contributing to uh, uh, which particular element in the matrix. So taking everything in account, you will get a stiffness matrix. And this will be like simply numerical values, because these are like easy to calculate uh, easy to calculate integrals. So you can see here, this is basically uh, a linear elements differentiation. So linear elements differentiation will only, like, the coefficient will remain, and like multiplication of that integrated over the domain, so you will get a very finite value, like evaluatable value, easy to evaluate. So you will get this kind of an equation. So what we are left with? We are left with this very nice form K. So this is called the stiffness matrix. This is the stiffness matrix multiplied by this T. In this case, this is temperature, but this is generally called the displacement vector. So this is basically the way this is. These are named is by comparing this to a spin mass system. So spin mass system, generally you have some F is equal to kx kind of a pattern. So similarly, this is called a displacement vector, and equal to, you will get an F, which is called, which is a force vector. So this you have, plus you have a very nice column vector where you have this, and you have all the zeros in between, and you have at the last uh, node, let's say nth node, you have this plus. Hmm. So can you tell me, like, if there are n nodes, this will have how many elements? N elements. So this will be T1 to Tn. And what about the stiffness matrix? It will be similarly n cross n. But how many elements are there? N minus 1. Because, like, if you have a linear element and you have like this n points, you can see there, like this, the first point and the last point both are there. So you can understand there are n minus 1 elements. N minus 1 element. And when the nodes are. Now let's talk about what we will do with this, like q double dash 1 and q double dash n. So we are definitely going to put boundary conditions. Now we know that there are two types of boundary conditions, right? So one is Neumann boundary condition. Neumann boundary condition. What is this? This is basically like mentioning the heat flux at a particular point. Let's say in the first point we mention this. So this is nothing but Q1 double. So if you mention Q1 double dash, we can simply put the value here Q1 double dash, and we can solve the expression. So nothing but basically, like in this vector, if you want to incorporate, we will simply replace my F1 element with F star, F1 star, which will become F1 plus F1 minus this Q1 double dash. So Neumann boundary condition is very easy to solve. What about a Dirichlet condition? What is the Dirichlet condition? Basically, let's say in this Tn point, I have a temperature specified, which is, let's say, T star. That is a Dirichlet condition. So I have, if I have flux specified, that is Neumann, and if I have the value of the dependent variable itself specified, that is called the Dirichlet. So if we have a Dirichlet condition like Tn, we uh, specify it to be some P star, then what we can do. So now we do not have we have a q double dash n, so that is a little bit tricky for us, but we can have a way around this. So we already know, like if we have this n cross n matrix and this n displacement vector and this n as this force vector, how many equations are there? There are n equations and there are n variables. If we have like n variables, so t1, t2, and tn. So these are n variables. So n variables, n equations, this is solvable. So what we can do is basically reduce one of the equations. So if we reduce one of the equations, let's say in the last row of this stiffness vector, so the stiffness matrix will have some values, right? Generally towards the diagonal, FEM matrices are always like you will have very it is called a sparse matrix where most of the elements will actually be zero. So away from the diagonal, these elements will be zero, mostly zero. And towards the diagonal, you will see the elements are there. So there are different types of elements. So the last row, since we are taking the last point here, so last row, whatever was the last row, I can replace it and write 0, 0, 0, 0, and last will be 1. So if I do this, what does this equation left hand side become? Left hand side becomes basically Tn, right? All like T1, T2, everything is multiplied by 0, and just the remainder is this Tn. So this left hand side, the whole equation becomes Tn. So Tn equal to, I will have Fn here and Q double dash n here, right? So let's replace all of them and simply whatever the Fn was, I will replace it with T star. Then what will be my last equation? My last equation will be simply Tn equal to T star. So we can do that, definitely that is doable, and if we do this, then our boundary condition will be satisfied, and there is no penalty for doing this because we will not have any uh, like uh, means we will still have n minus 1 equations to solve n minus 1 variables if we are simply substituting the value like this. So this is one way, but this is actually a little bit trickier to implement uh, in computer code. Like this is definitely not impossible. We can very easily actually implement this, but this increases the there is a better way to do this. Instead of simply editing the whole stiffness matrix, there is another way to do this, which is simply that if we take this corner element, so we have whatever the matrix we have. So the rest of the matrix is there, whatever the value. Just we take the corner element. Let's say this is KNN. So my new KNN, let's say that is KNN star. This will be equal to my old KNN plus L. What is L? L is a very large number. So L is a large number. How large? It can be arbitrarily large, but finite value which a computer can understand. Because the only reason we are doing such a method is to have a computational advantage. So anything that computer can read very well and easily, and it is large, we can simply add it to it, and then oh, okay, all right. So we were discussing about the boundary conditions, not much. Okay, I will discuss the Dirichlet part again. The Neumann was all right, right? Neumann was audible. The Neumann condition you had heard, right? All right. Since I'm like writing in some other screen, it is very difficult to see your the like messages. You can like speak up as well. That will be helpful. Okay. So let's restart. All right. Start. Um, so we have this kind of a condition. I'm not writing the uh, Q double dash part. If anything is required, then that like you can assume it to be included in F. So, for example, if there is any Neumann boundary condition, you can assume that I have already included that in F. So, what I am here like now talking about is, let's say we have a Dirichlet boundary condition. So, what is a Dirichlet boundary condition? Dirichlet boundary condition is when you have a temperature specified at n. Well, like let's say in the first point only. So let's say for the sake of it, let's say T1 is equal to T star. Okay. So this is basically another equation that we have. So there is a way that like what I was discussing is basically like I can simply substitute one of the equations from this set of equations. So this is like set of n equations. I can substitute one of these equations with this, hoping that the other equations are solvable, and I can implement my uh, condition, this boundary condition, like using that method. So, so let's say if like T1 is specified, we would prefer that the row 1 to be substituted. We can substitute the row 1 in such a way that the diagonal element here is the first element. So that is 1, and the rest all are 0. So the rest of the matrix stays intact. So this portion stays intact. I am not touching this portion. I am just playing with the first row. So this is 1 and the rest all are 0. So what will that make this left hand side? So left hand side is basically T1, T2 and so on. So this left hand side now becomes T1, just T1, because 0 is multiplied with all of the other temperatures. So this is simply T1. What is this equal to? So I can simply substitute this F1, whatever this F1 value was, I can substitute it with T star. Next, you can have this F2, F3, and so on. No problem. Just the first element, I can like because the first element has this boundary condition, I can substitute with T star. So I will have T star. T1 is equal to T star. All right. So this basically is was our boundary condition, and we have successfully implemented it within our matrix framework. So there is no problem there. But the thing is, in like when we write our computer codes to solve this FEM method, if you want the same code to be able to like solve for the Neumann as well as the Dirichlet condition, there is a better way to do this. What is the better way? So we can simply like if my point one has this condition, then I can simply say in this K matrix, I will take the element K11. What is this element? This first, the diagonal element K11, and I will like replace this with K11, whatever the old K11 was, plus this large value L plus yeah, so the large value K11 plus L. This I can replace. Uh, I hope the connection is there. Yes. So yes, I can replace this like this, and I can also replace this F1, whatever the F1 was. So this has F1 star F1 plus this large number into P star. The reason I am doing this, now let us see what my equation, this matrix, the first row of this matrix equation becomes. Now, what does it become? This is K11, K11 remains, right? So K11 T1 plus I will have K12 T2 and so on. I will have all these terms and I will also have this large number L multiplied by T1. So this was with K11, so this is multiplied by T1. And here what I will have? I will have this F1 plus LT star, as I have already like mentioned here. So let's say if L is very large, then all these terms, these will be negligible. If L is very large, let's say like 10,000 or so, and the other terms are in the order 1. So if the difference is of that scale, then I can approximately say that the equation that I am doing is nothing but L into T1 equal to L into T star, which is nothing but T1 is equal to T star. So this is another way that this boundary condition can be implemented. This is called the penalty approach. Okay. So so far what we have done, let's recap a little bit. We have, like, in the finite element method, we have seen how we are like solving this problem over each small element that we have divided the domain into, and we have used the Galerkin's method for doing this. And then we have converted this Galerkin's method into a matrix form. And using this matrix form, we have assembled all the elements into a combined matrix, a large matrix. And then we have also seen how we can implement the boundary conditions, different types of boundary conditions within this matrix system. And thus we have, like, so far covered a basic preliminary knowledge of what is finite element method and how we implement finite element method in different situations. How we will solve this? This is very easy now. This is simply a set of linear equations. So there are definitely a lot of ways to solve this, and like, there are literally separate courses on how to solve this efficiently. So you will have um, scientific computing and courses, which will basically, the whole course will be about how to solve this kind of an equation. And basically the objective is to find an inverse of k, so that the problem becomes this. So the whole computing struggle is basically finding k inverse. How efficiently we can find k inverse, that basically gives how efficient the computer program is. And this is basically the finite element method. In any methods that we are doing, like, finally we do achieve this kind of a matrix equation, and finally we do have to find the inverse of the stiffness matrix. Okay. So this was a brief about the finite element method. Let's, like, there are very simple questions, and let's, like, look at them first. Then before going to the next element, we can take a small break. Okay. So can anyone please answer this question? A simple question: 1D domain divided into 10 elements. So how many? Yes. What will be the size of stiffness matrix? So 11 cross 11. That is absolutely correct. So 10 elements means 11 nodes, and 11 nodes means it will be 11 cross 11. There is no ambiguity for this. Okay, let's look at the next question. Yes. So this is about the penalty approach that we just described. So which one is the correct statement? So this is for the Dirichlet boundary condition, right? B. B is adding a large number to the coefficient of the boundary node term in the equation pertaining to the boundary node. That is yes, that is also correct. So what we have is excuse me. What we have this is the stiffness matrix and the diagonal term which which corresponds to this particular node. There we will add a large number, and also we will add a large number to the force matrix, right? Uh, so if we do that, then we will if the number is sufficiently large, only that part will dominate. So that is basically the concept. Okay. So this is a comparatively longer statement, and I would suggest that you do this particular problem. You attempt this problem because this will help you to understand this method better. But this is a little bit longer. So what you have to do is basically solve uh, an FEM problem. So it is given you have from 0 to 3. So at x is equal to 3, p is specified. This is 50. And at x is equal to 0, what is specified? dt dx is specified. That is 0, which means flux is 0. So now you have to find at x is equal to 2, what is the value of t using FEM. So what you can do is basically do a 4 element FEM problem. So you will get a 4 by 4 matrix. You can write a code also if you if you are good in programming, you can easily develop a code, write a code and solve the particular problem. I will ask you to attempt this. If you can do it by hand also, but finding inverse of the 4 by 4 matrix will be a little bit challenging, but that is also doable. You can take help of a calculator as well. I guess you will. Or online also, you can help like take help of online calculators as well, which will help you to find out the inverse of the matrix. So you take these 4 nodes and 3 elements, follow the steps that we have discussed, and you will be able to find. Do this problem. If there is any difficulty, we can discuss this later. Got a bad code. All right. Is there any question regarding FEM? We will move to the next part now. We will move to finite difference, and hopefully I want to start the discussion of finite volume as well in today's session. Okay. All right. Just take a short break, then we can start. Okay. start. Okay. So far, like we have been discussing FEM mostly, and we had discussed our weighted residual approaches. You will find if like finite difference and both finite difference and finite volume, like the initial concepts much simpler than the other two. The like previous methods are more in depth and mathematically involved, but that does give you a like good idea of what we are trying to do and what means the rigor, basically the mathematical rigor that is there in like in developing these methods. And this is like also like will help you appreciate especially the finite volume method, since you have already learned this finite element and uh, weighted residual approaches. So let's like discuss the finite difference method. Then like this is the simplest or the most simple. You will find it the most simpler method. So, so let's say we have a point x, we have x plus h. We have So here basically we are so these are generally in this case we had some certain nomenclature in our finite element method. We used to call certain points as nodes and certain points as elements. Here we have grid points. So these are grid points. And there are step sizes. So H, this is like basically the uh, step size or the mesh size, whatever you want to say. And in this case, in finite difference method, the smaller h you will take, the more accurate your solution will be. Let's say, what is this basically basing it on? Like whatever equation you have, you will have certain differential equation, and what we will try to do is like make a algebraic expression out of it. We did the same thing in finite element method. We took the differential equation, and at the end of it, we arrived at an algebraic equation, right? So this is basically an algebraic expression. So here in finite difference, we will do the same thing, but with a very straightforward approach. What is our approach? We will simply take the Taylor series expansions. So uh, we know the Taylor series expansions. Just let me write it down. For like let's say for any function f, we if we try to evaluate x plus h, we can use the derivatives at f of x to find it out. F double dash x plus you will have higher order terms. You will have h cube and so on. And this is an infinite series, so this will go on till infinity. It converges to a value, and that value will be fx plus h. Okay, so this is the the concept the like of Taylor series, and you know that if I like truncate it, let's suppose I truncate it here, then how accurate is this? This is accurate with an error of the order of h cube. So next term will be h cube. So next largest term is h cube. Something multiplied by h cube. So we will say this is like if I truncate it here, it will be accurate up to h square. Okay. Now, in this method, we are not really bothered about finding f of x plus h. We want to actually evaluate the derivatives f dash x, for example, using this method. So we will let's first what we will do is trying to find f dash x itself. So that we can. like rearrange this and you will find. So I took this side, divided by h, and I will have minus h by 2 f double dash x and so on, other terms. So let's take only this term. So if I truncate it here, let's say, if I say I approximate my f dash x as then what will be my error? My error will be of order h. Right, because the next term is h multiplied with something. So h I can take it as small as I want, and like the smaller I take h, the less the size will be of the error. Okay, that is basically the concept. So instead of taking the expansion of this if x plus h, I could also have done the same with f of x minus h. Okay. So here also write down this series expansion. Here it will be like changing signs, right? I will have minus, then again plus, and so on, and so on. Okay. So from here also, I can find out f dash. This you will see is this you will see as f of x minus h divided by h, and uh, yeah, and this will have plus h by 2 f double dash x and so on. So here also, like if I approximate up to this term, then I can say that I have order. So this is called backward difference, because like this is x minus h, so it is like a backward point. So that's why like the name sticks. So this is backward difference. Backward difference is basically like if I have a point, let's say I, then I take the difference with reference to like I minus 1, the previous point. And this is the forward difference. And you know that there is a central difference as well. So what is the central difference? The central difference will take this equation and we will take this equation, and what we will do is subtract it. So this equation 1 minus equation 2. Then if I isolate this f dash x, what does this that become? That becomes f of x plus h minus f of x minus h divided by 2h. So h f dash x minus of minus, so plus h f dash x, so that will give us 2h. What will be the order of error? You see that h square f dash x will actually cancel. So the next term, whatever will be there, will be of h cube. That will remain. The h cube term will remain. So h cube by 6 plus h cube by 6, that will be h cube by 3. So that will remain, and you will have divided by 2h. Uh, so the order of error will be h square, right? So h cube you have, if you divide it by h, the order of error will be h square. And so the order is much lesser here. So if you have h equal to 0.01, let's say. So in forward difference and backward difference, your order of error is 0.01, like in the second place of decimal. But in this case, your h square is actually 0.001, right? 10 to the power minus 4. So order, the error's order is much lesser here. So you will have less error. This is called central difference. These are the main concepts here. So what we do is simply take Taylor series expansion and try to like eliminate uh, the terms to find out the derivative that we need. We can similarly find out the second order derivative as well. How we can do that? We can take this equation 1 and 2, and if we suppose we add them, if we add them up, you will see the f dash terms getting cancelled, right? F dash terms will get cancelled, and you will be left with fx plus h, fx minus h, and fx. So you will get a nice equation with the functional values at this point, and you will like find out f double dash. So that is basically the whole concept. Okay, if there is any question, please like let me know. What a very bad code. All right, we can like discuss some questions. So this is also basically like the questions based on concepts of this finite difference method. So the question is finite difference approximation of the first order derivative of a function f at ith grid point using the forward difference scheme of first order accuracy gives grid points I and I plus 1. If we intend to find the same first order derivative at the same grid point using a forward difference scheme of second order accuracy, then the grid points involved will be what? Okay, so what does it mean? What does this question mean? So the question means that like for first order accuracy, what is first order accuracy? Order of h. If the error is order of h, we saw that for order of h, I plus 1 minus fi divided by h. This gives us f dash x, right? Now, if I want to do order h square, we saw central difference method. That is one method that we can do. But let's say we do not want to use like I plus I minus 1 here. We only want to use like let's say the points which are after I, like I plus 1 or I plus 2, or like even further. Then what will be the like what will be the uh, terms that we will be using? Is the question clear? Is the question clear to you? So here basically what we will be using, we will be using the next point. We will use I plus 1 and I plus 2. So how we will do that? This we already know. F dash x plus x square by 2 f double dash x and so on. So if I use the next point, which is like this, what will be the Taylor series expansion? Plus 2h f dash x plus h square. So this is 2h, so this will be 4 square. 4h square by 2 f double dash x and so on. Yeah. So yeah. What is my task here? My task here is to find f dash x and second order accuracy. So second order accuracy means I will try to eliminate this term. So this is like a simple algebraic problem now. So here h square, the coefficient of h square is 2, and here the coefficient h square is half. So what I will do, I will simply multiply 4 with this equation and subtract. So if I multiply 4 with this equation and subtract it, what will happen? This particular term will get cancelled. So I will have 4 f of, let's write it like this, minus I plus 2 is equal to 3fi, right? 4 minus 1, so 3, plus here will be, this will be 2h, right? 4 minus 2, 2h f dash x. This is what we are trying to find. This term has got cancelled and others are higher order terms. So I can simply rearrange my f dash x in this way. 4 I plus 1 minus fi plus 2 minus 3fi divided by 2 plus order of error will be, so h square term we had cancelled, so next term would be h cube and we are dividing by an h, so this will be h square again. So its order h square we have found out using points I plus 1, I plus 2. This is a forward difference method, so we will not be using any of these I minus 1, I minus 2 or I minus 1, we will not be using. Okay. All right. Okay, very similar question, please try to attempt this one. So here the same thing is asked basically. A second order accuracy we will try to find with a backward difference. So what will be the answer? It won't be I plus 1, it won't be I plus 2, it won't be I plus 1. So only this is our option that is remaining. So this is the option that is remaining and we will use this. This is our backward difference. Okay. All right. So similar question again. So central difference scheme is there, and here it is asked about second order derivative. So second order derivative with a second order accuracy. It is asked which grid points, how many grid points will be required. We will use a forward difference scheme. So we can calculate this, no problem. But we can also use the like definition of such a forward difference scheme. So forward difference scheme will always have I plus 1, and so on. I plus 2 will never have I minus 1 or such. Okay. So we will not have this. A will not be there. B will not be there. D will not be there. Only C will be there. Now we can also try to like understand why there are 4 points here. So here you see what we have to find. We have to find F double dash X, right? We need to find F double dash X. So for the with a second order accuracy. So for this we have to eliminate F dash X. Yes, because we cannot have like F dash X within our scheme. We need to find it using the values at the grid points. We cannot use derivatives at the grid points that we are finding. So we can only use the values at the grid points like F of X plus H, F of X plus 2H. These values.
Hello, sir.
Yes, please.
Sir, hello.
Yes, please, I can hear you.
Sir, sir, can you repeat how do you select that option C
In which question? This
for
particular
this?
question?
Now you presenting no, sir. You shown the answer is option C is correct.
Yes.
How did you select that one? Can you repeat that? Why do you
Yes,
select this
sure,
one,
sure,
sir?
sure, sure. Like basically here I like selected the answer first using an elimination procedure. So it is already given. We need to use a forward difference, right? And by definition, forward difference scheme will always have the point and the point after it, right? So it will have I plus 1 point, I plus 2, and so on. But it cannot have I minus 1. Then it is no longer a forward difference scheme. So that logic I have used. So with that logic, option A will not be correct because it has I minus 1. Option 2 will also, B will also not correct because it has I minus 2. Option D has I minus 2. So these are not correct. However, option C is the forward difference scheme if we make a forward difference scheme of that. Okay. So this is one way to answer it, and now I am trying to discuss actually how I will find out a second order accuracy derivative. And how do I know? Like if the options were a little bit not in this way, then how would I know how many values do I need to find a second order derivative using a first second order accuracy? Okay, so let's try to understand this. Okay, so for that, let me first actually let me start over. So let me first write down the a Taylor series expansion. Let's say of fx plus h. So I have fx plus h f dash x plus h square by 2 f double dash x. Let me write one more term h cube by 6 f triple dash. All right. So now what do I have to find? I have to find f double dash x, right? This is what is asked. So if this is asked, then I definitely know I have to divide the whole equation by h square. So I have to divide the whole equation by h square. Now what is asking? It is asking a second order accuracy. So if it wants a second order accuracy, then what is second order accuracy? The expression should be accurate up to uh, like h, and the error will be of the order h square. So for the error to be of order h square, what is the term till which we have to take? We have to take till this term, because after this will come h to the power 4 by 24, right? So that will come after this. Okay, so this term will give me h square after division by h square. So h to the
Sir,
power 4.
voice not audible, sir.
Okay, so the internet is very disturbing today. Like we have. Can you hear me now?
Ah, yeah, sure, sir.
Okay, okay.
Thank you, sir.
Somehow got muted. Okay, thanks. Can you see the screen? Yeah, I hope the screen is visible. Okay, so if x plus h, I have written down this Taylor series expansion, and I'm trying to discuss like how I can get a second order accuracy for a second order derivative. So I have to find f double dash x. So to find f double dash x, I need to divide this equation by h square at some point of time or other. I will need to divide it by h square because I have an h square multiplied with it. What does second order accuracy means? Second order accuracy means the error must be of the order h square. So what I like find is I have to work till my third order derivative term. I have to eliminate this term. Otherwise, my like h square term will only come in the fourth order derivative, because there I have h to the power 4. So h to the power 4, when I divide with h square, that will be h square. So this I can eliminate. But this till third order derivative I have to consider. Okay. So, which are the terms that I need to eliminate? I need to eliminate f dash x, because f dash x should not be there. This is a derivative, and I need to find only the f double dash x only in the expression which contains the values at the grid points, like f at x, f at x plus h, not f dash x. I do not want any derivatives in my expression of f double dash x. So f dash x I need to eliminate. I also need to eliminate f triple dash x. This also I cannot have it in here, right? Because this will increase my error order. So if I need to eliminate two terms, how many equations I need? I need three equations, right? I need three equations so that I can eliminate two terms and get a resultant equation. So how many points will I need? I will need these 3 points on which I am performing the Taylor series expansion. These are the points where I am performing the Taylor series expansion. And I need f of x itself, right? I need f of x itself. At that point, I definitely, that point should be there in my expression. So this is also there. This is the point, basically the focal one, the point that we are like calculating. So that this should be there. So 3 plus 1, total 4 points should be there. So that's why you see here 4 points are there. So these 4 points are basically essential to find out second order derivative in second order accuracy using forward difference. Okay. All right. Okay. If there is any question, please let me know. Otherwise, I will give you a very short introduction of uh, this finite volume method. And today we had a lot of like disturbances with the like internet connection as well. We lost some time there. All right. So we have discussed FEM. FEM, what we are doing in FEM, we are dividing the domain in elements, and we have nodes, right, which are basically the border of elements. We have these elements and we have these IJ nodes in FEM. Okay, we can have different shapes of these elements. Like for example, in 2D, like this is my domain. I can divide this up into let's say triangle shape, right? I can do this in FEM. This is possible. Uh, After that, we discussed FDM, finite difference method. What was that? We had grid points. We had a grid-like system. So we had like x minus h, x plus h, x plus 2h, and so on. So this kind of a system, an array kind of a system. And what we use is Taylor series expansion. So we can also write the fundamental that principle that we use. Here we use Galerkin's method. We use Galerkin's method. FDM, what we use Taylor series. Now we are going to learn about finite volume, FVM. And this is actually very pivotal to understanding CFD problems, because most of the CFD codes that you will popularly find is based on FVM. Though nowadays, like there is also a shift towards like FEM based codes. FEM is like very useful in certain cases. It is also mathematically very robust. But if FVM has been like in majority cases the go-to code for solving any fluid mechanics problem. In CFD problem, FVM is the go-to method that we use. So FVM, what happens is we divide our domain into control volumes. So let's say we have a 1D domain, as we have all like studied 1D domain for other methods as well. So let's have 1D domain. So these are control volume. So CV is control volume. This is like corresponds to element in a like finite element. So this corresponds to element, and we also have this centroids of the each control volume. These are like grid points. These are also like called grid points, and you can call them as grid points. So these are very similar to like FDM grid points. So unlike in FEM, we do not have like nodes at the edge of the each discretization. The discretization here being control volume, we have it at the middle. We have it like uh, at the centroid of the control volume. Okay, and what is the the principle that this method is based on? This is also like very different from others. This is based on conservation law. So what we are like in this particular method, what we will basically do is like solve a kind of very similar to a conservation law. Huh. Like a value of a particular variable will increase only depending on the like source and the flux from the other elements. Basically, a Reynolds transport theorem applied to very small control volume. Okay, so this is the basic like fundamental principle, and you will see like why this is appealing to fluid mechanics is because of the same reason. In fluid mechanics, we deal with conservation laws. All the fluid mechanical equations are basically conservation equations. We have momentum conservation, mass conservation, species conservation, energy conservation, and so on. So all of these are conservation equations. Whereas like FEM, it is Galerkin's method. These methods are basically minimization problems, and they are more suited towards uh, like for example structural mechanics. You will have like minimization of potential energy, or in dynamics problem you will have a minimization of the Lagrangian. So in those like problems, FEM will be very suited, and will come up naturally basically. And in fluid mechanics, FVM comes up naturally because this is also based on conservation principles. So, uh, so let's try to understand what happens. Let's take one element, for example. So, uh, by element, I mean control volume. Excuse me. So, this is the control volume, and its center, let's denote it by P. So, it also has a like its own notation kind of. So, this point is almost always represented by P. Like any textbook, you will find this almost the same notation. The neighboring elements are noted as east-west, given this kind of an east-west kind of an. So to the right it is east, and to the left it is west. So these are basically W and E are points in the next control volume. They are not inside this particular control volume that we are focusing on. They are basically the adjacent control volume central points, and those will also be important as you will see. And here we can take the length of this particular element as delta x, control volume as delta x. We can also name the edges. So east edge small e and west edge small w. So if we have 2D, we can like name it north, south, etc. Uh, we can also handle complex geometries in this particular like method, uh, and like nomenclatures will vary at that time, and it might at a certain point be more useful to like number each control volume. But for demonstration purposes, we can always use east, west, north, south as has been the convention. Okay, so this delta x distance is important, as well as two other distances are very important. P to E. So P to E distance. This distance is denoted by delta x E, and similarly P to W. This distance is denoted as delta x W. And these are the different lengths and things that will be important. Okay. So any equation that we are solving in this case, we'll try to like find out the variable, like let's say x is or let's say y will be a more appropriate term. So y is, let's say, the dependent variable. So y of p, this we will have certain coefficients, certain like a e ye plus some aw yw. So these are what? These are fluxes plus some s, which is source. So something like a body, like some generation term. S is some like heat generation or reaction mass generation, or it might also be like body forces in momentum type scenarios. So this is basically the ideology. We develop like try to estimate point P uh, using the neighboring fluxes from the neighboring control volumes and a source term. Okay, so we will like very quickly try to demonstrate that for equation we were generally using for such demonstration. This is our familiar steady state conduction equation with a
Sir,
yes, please.
so here what does YP denote, sir?
Yp is basically the unknown variable. So I have not written down the equation here, whatever the equation might be. Okay.
Okay, okay,
So
sir.
in this case, it is temperature. So Y is basically T. So what I am trying to say is the philosophy. So the philosophy here is I will take some fluxes and have a source term. With that, I will try to estimate my Yp, which is the like value.
So that is not P elect number, sir.
Uh, can you say again?
That's not a P elect.
That is not a P. What?
P elect number.
No, no. This is like this Y at P, basically. Okay.
Okay, sir.
Oh, yeah. So yeah, we come back to this. Okay. We are trying to find out the resultant such algebraic equation for a particular finite volume. So P. P okay. The lengths are there. We have already mentioned. Like okay, let me write down delta x. This will be delta xe. This is the notation that I will you might find slight variations in notation using this lens for in different books, but like this east to west thing will be there in every book that you will see of finite quality. Okay. This is E W. All right. So this is what we have got so far. Now what we will do is basically uh, since this is a conservation equation itself, we will try to integrate this and try to find out like the surface variation of this. Like if you recall deriving this equation in like heat transfer class or like similar equations in fluid mechanics class, those who have taken such courses, we like used to derive this using such concept where like we we take an element and we try to find out what will be the flux in and flux out and generation. There will be some generation. So we will try to balance that. And same thing we will do here. Basically, we will start from the equation that we had derived itself and try to find the equivalent like flux in, flux out kind of a formalism. So we can simply do this if we integrate over this control volume. This is 1D, so dx. Okay. So this is integrated from west to east, as is the convention. So you'll see this is very similar to your finite element method or like weighted residual method basically. So weighted residual method is basically you multiply a W here. You multiply a W here. So here you can say that W is 1. Mm. So like a finite element method was also a weighted residual method. That was the Galerkin style. So W, the weighting function was uh, defined according to the trial function. Here the weighting function is taken as 1. So this is a weighted residual method, just a different method of finding out the W. All right. Okay. I will erase this. This might be confusing as there is a W here. All right. So let's try to solve. So the first term is basically ddx is there and dx is there. So this will be simply evaluating this dtds, which is flux, and that's what we want, right? We want to find this whole thing like as a balance of fluxes. So we get this here. We get this here k dt dx. Uh, so this is at E minus k dt dx at W, right? Plus, if S is constant, we can simply take this out, and dx, the integration will be S. This is equal to 0. So this is our equation. Very straightforward. Now our um, task is to basically find this dt dx at E and dt dx as W in terms of this PW, PP, and TP, right? Otherwise, how we will get this algebraic type equation? We need to find this algebraic type equation, which we can assemble to form a matrix kind of a thing, like we did in the finite element method, and then like calculate the inverse of the matrix and like find out the values. Okay. So for this, what we will do is basically take a trial function like we did. So here this is better known as profile function, profile assumption basically. So uh, uh, we will assume a particular profile of temperature. We might take linear. The simplest case will be linear, and we did that same thing in the finite element method also. We took linear elements. We'll take such linear elements and try to calculate. Okay. Uh, so let's do one thing. Since we are already running out of time, I will pick up like right from here, and we'll try to cover a little bit more in the next class because we lost a lot of time in this session. Okay, uh, and like please like prepare like any doubts you have regarding if finite volume element and like any other portion that we have covered so far. All right. Okay, thanks for joining. If you have any question, you may ask right now. Okay, so I'm ending the session here today. We will like continue in the next session. Okay, thank you.